Hello everyone and welcome. This is going to be a submission for my final project for a advanced graphics course which I'm currently involved in, and also sort of as a in progress research report because this software will turn into a research project down the line. So to get started, the overall goal of this project was to build a renderer in Vulkan to render different volumes, and for this I wanted to use a path tracing algorithm. So for this, I decided to use a library called openVDB, which is used in industry all over the place to represent different volume fields or particle simulations. You can see their homepage here. They have pictures from like a whole bunch of different DreamWorks projects, and they're used by Pixar and a couple other huge studios and companies. So basically the overall idea of this library is that it provides a memory efficient structure to represent sparse volume fields or particle simulations. So the idea could be that you could create your particle field or volume simulation in a software like Houdini and export it and then import it into your ray trace based renderer or whatever other renderer you have to create your final look of your simulation that you're looking for. So this interoperability is fantastic and is the foundation for why a lot of other big open source libraries are popular in the rendering world. And since big companies use multiple different softwares in their rendering pipeline, that's why these are necessary. But it's also great because, it allows more flexibility for how you create stuff, because you don't actually need to create the simulation software. If you need to simulate particles, you can use something off the shelf like Houdini. But anyway, the foundation of this is Ken Museth was the original developer of openVDB, or he did a lot of work on it. And this is a paper that he published, I believe, after openVDB was finally released. But this kind of goes over the idea that that VDB grids are built on. And won't go into too much detail here because I don't want to go too long. But the overall idea is that this is a sparse grid that kind of looks like a B plus tree and has a lot of, but instead of that, it gives you constant lookup time. And it takes advantage of the idea of what parts or voxels of your simulation are active and inactive in order to save some space. So this is a great little reference if anybody's curious of looking into the underpinnings of this library. But for us, we're just after using it. So to give you a look at what some of these look like, this is Blender. This is their renderer for a openVDB volume, and this is simply a sphere cut into the middle of a cube here. So the overall render that I'm going to be presenting here will look significantly different than this, just because of the different approaches that are taken in computing the look of the final density field. But in order to get started with this, I'm going to be walking you through how to set this project up. So we're going to go to that next. So to get this set up, you have to do a couple things. The first step will be to replace, if you open up this prep.sh file, you need to replace this vcpkg underscore path string with a path to your install of vcpkg, and I already have that there, so I'm going to go ahead and just Control Z so we can have that. And then this is going to actually go through and build the debug and release versions of openVDB. So I usually do this. There is a bat file here too. This is more for the older way that I had this set up. It's similar, but there's a couple variables that are different. And I suggest you just use the bash file, even on Windows. And the way I do that is with the git bash terminal. So we'll just go ahead and run this. And then once this is done, there will be a couple new folders, prep_work and a libs folder, and then also a vcpkg installed folder. So the prep work one you can delete after if you really want to. It's just like the cmake directory, config directory. But then the libs folder, which won't be here until it's done, is what we want, because that'll be the install locations for openVDB itself. So once that's done, we'll come back. All right, so after the setup script is finished and you see all these installing messages up here, There should be a libs directory, and in here's a debug and a release. So after that, we can, if you're on Windows, we just have to make the Visual Studio project, which you can see there's a command in here for in the prep.bat file. I didn't put it in the sh file just because this also is used on Linux, so obviously you can't create a Visual Studio project on Linux. So anyway, what I usually do for this is I just make a directory, and then we just go ahead and pop that in there. And of course, make sure you add your path to it. And then it will go ahead and generate your Visual Studio project. And I will come back again after this is finished, because this can take a little bit. All right, once we have, once that build is finished, you go ahead and go into the VS project folder that we just made, and Starlight App, Solution, and open Visual Studio. And there's one more thing we have to do to finish this setup. You want to go over here into the Starlight App Solution, hit Properties, and we need to enable VCPKG. So you want to hit Yes for Use, and also Yes for the manifest. And since I'm going to be building the release version of this, leave it on Release. And then switch this to Release, and set this as Startup Project. And then you can build the project, and VCPKG will install everything. The only thing that you have to do once it's done, to make this easy, we won't wait for it, is you go to that libs folder that was just made for openVDB, and you want to copy the corresponding version or build type. So we want release bin, and there'll be this, openvdb.dll, and you just want to copy this to wherever the build directory is for the actual application. For this specific instance, it's under vsproj, and there will be a release directory in here once it's done, and I'll just copy it in there. But for brevity, I'll leave that out, and after this we can get to talking about the actual project. All right, so once you get everything all set up, this is the scene that you'll be presented with, and the controls for the camera are very similar to before. You can click and drag on the screen to move the camera around, and WASD to move the camera forward, back, left, and right. Okay, so as we can see, we're presented with a cube here, and the term represented as these red lines. And this is the axis line bounding box of the volume that we're about to render. This current implementation uses a Raymarch-based algorithm that is currently single-threaded on the CPU, so it's a little slow. That's a future expansion that I'm looking to make, where I write it into a compute shader to make this a lot faster, or multi-thread it using something like Boost. But anyway, the first step of the Raymarching algorithm is to cast rays from the camera and hit the axis line bounding box, because in order for us to sample the volume, which is the whole point of the Raymarching algorithm, we have to measure the distance where a ray enters and leaves the volume. So we can actually visualize part of this by setting the Raymarching of the volume to hit the axis line bounding box. So that's done with K. So if we hit K, that will actually set the next render of this to hit the axis line bounding box and just return a red color. So the reason why it doesn't automatically do this is that this, by the way, this is raster, is what we're looking at right now. It's because the Raymarch algorithm can be a little slow, especially with the current implementation. So we're free to move the camera around, and in order to actually trigger the render, we would hit H to trigger the render, and we can actually see that the rays have hit the correct dimensions of this bounding box. Now, if we try to move the camera, you won't see any change. But if we hit V to change the visibility, you will see that the volume has moved, and that's because the camera can move while we display the volume result, render result, and that's just a little fallback of this program as it is right now. So I can show it from this angle. If we hit H again, that will draw the volume, and we'll go ahead and show it and display it a couple times. And we can move the camera around a little bit again and hit H again, and that will render it. So once we actually have the rays entering and leaving the volume, we can measure that step distance. So we go ahead and measure it, and then we can define a step size. And between that distance, we sample the volume along each of the steps. And at each step, we then for the light that's currently in the scene, we draw another ray from that point that we're sampling to the light itself. And then we do another sample along that distance. And at each step, you're sampling the volume, density again, and calculating the effects that the light will have on that point that you're currently sampling. And then once you've done that for all of the, from your sample point to your light, you can then sum those up and then do that for every point along your ray. So it's quite a bit of work, but due to its nature of it being done for each pixel on the screen, you can separate it out and parallelize it for each ray, which is how most implementations of this work, at least in production. And that is a future thing of the future implementation of this software. So we're going to go ahead and do that. So to set the normal ray marching, you go ahead and hit M, and that will trigger the next render to be set as normal. And we'll go ahead and hit H to render it. In this scene, the light is currently directly above the volume. And this volume is, as I showed previously, or might show after again, the Blender, in Blender, it was the sphere looking render. So we'll see a little bit of a sphere shape and the actual bounds of this volume. So I'll go ahead and hit H, and that will begin the render. And this does take a couple minutes. So we'll come on back once that is done. Okay, so once that returns, you'll see this big white glowing volume. And this is our sampled volume that we have just produced. And as I showed before, or will show in a minute, you can actually see the sphere edges right here. I'm not sure how compressed YouTube will make it, but you can see the overall circle that is from the missing densities within our active volume, and that is defined within openVDB itself. And the look of this, how bright it is or whatnot, can be changed depending upon different parameters that we provide the volume. And I can show you where that is at here in a minute when I actually do the a little code review for you. But currently, with the settings right now, I was looking for a way of trying to get this circle to really show up, and that was accomplished. But with these settings, you can see the actual edges of the volume here. And because this current setup is with the light directly above the volume, you'll see that the top of it is brighter than the volume, or sorry, is brighter than the bottom of the volume, because at the bottom, the samples have to go further and further up. And because we're so far from the light, the actual impact that light will have on that sample point is very small compared to the top of them, compared to the ones at the top. So if we hit H again, that will begin another render. And because I just did that, we're now stuck for another render. I will go ahead and close this so that we can do another look at one more thing. Because openVDB is so flexible, what I wanted to try and display here is the actual active region of the volume itself. openVDB, when you create a volume itself, you can, or a grid or tree, you can define it as a volume or a different format. This uses a volume. So every space within the grid is defined as either being active or inactive, 0 or 1. And then in between those two active and inactive zones, there's a linear interpolation between 0 and 1, and that designates the boundary of the volume. So if we hit J, that will set the next render to be the active region of the volume. And if we go ahead and hit H, that will trigger the render. And this is very strongly it is the circle that we previously saw in Blender, because this is the actual region where those values are being interpolated between 0 and 1, and this is the boundary of the volume that was actually defined. So now we're going to go on to the code review. So I'm going to cut to that here in a minute. So I'm going to give a really brief overview of how this ray marching implementation was done, because if you go and look at the GitHub in the near future, it's very likely going to change because this is going to become an active research project for me to use. But if we look at this volume class, there's a couple things to look at, and this main part is render volume. And this is our entry point where we can calculate the boundary of our axis line bounding box. and we pass it to we first have to calculate the ray for each pixel on the camera, which is done via a couple computations for each ray, and we run our ray box intersect algorithm, and this is the slab method, as I said before. This can also be converted to or translated to a compute shader and performance. So we're going to probably look at doing that in the future. But if it actually does hit, we'll go back. It will give us a T0 and T1, which is our entry and exit points. And we'll be able to check if it actually does, it'll actually tell us if it actually hits by its true or false value returns. And these are the different render settings that we have set. So if it's the axis line bounding box, I just simply set the new color to red. And then it depends upon which value we have enabled. If we only want to render to the volume boundary, which is that active boundary in openVDB, we just call this function for forward march to volume boundary, and we're just checking to see if the sample density is in between 0 and 1, because that's the interpolation region, and then return a color that is red. Then finally, for the normal march, it's just called forward march. This is the ray marching algorithm, and the parameters for this are set in just different protected values for this, because I haven't quite decided if I want to be able to change this at runtime or before runtime or not. Theoretically, you should be able to change these whenever, because each run is independent. But you can set the step size for the main step through. That this is when a ray enters and leaves the volume, the boundary. Or you can set the step size for when it's actually sampling the light. I have this set much higher because we don't really need as much resolution in that regard. But that will be the step size from the sample point to the light itself. So you have to do that for each one. And these are different properties that are set for just the actual lighting calculations for how much impact a light will have on a specific point that you're sampling. And this is like a default volume density. That's really not used too much. And Russian roulette cutoff, this is a value that's a way of doing a sort of branch and bound optimization on this algorithm, in that once your step size gets so far into the volume, you can check if it's below a specific value, and you give it a chance or a probability that it will just kill it. So we can do random cutoffs just to try and give us a little bit of extra performance with that. This is a common way of trying to eke a little bit more performance out of this, but in the overall grand scheme of things, by the time it gets so small, you really don't get a bunch of return, ideally. But the Russian roulette cutoff is at the very bottom of the forward march within the actual for loop that goes through the actual number of steps that is calculated that we'll need to take in order to properly sample the volume for the defined step size that we have. Okay, and then random jitter. This is a way of trying to normalize the look of this too. What can often happen is if you sample from normal step sizes. So if you think about our grid, if you take a specific number of steps in every single direction, so every step size is 5, that can create like a very grid-like appearance and cause some very harsh corners. So that circle that we saw earlier could be very jagged. And the one way of trying to solve for that is by adding a little bit of jitter to your actual step size. So instead of stepping exactly 5 units, we might step 5.1 or 5.2 or 4.8. It depends upon a random value that we use. And that is calculated right here, how much random jitter we're actually adding to the step that we're going to be taking. And this is added to both the so this is added to our actual step of how far we're going to be sampling into our volume. And when we're actually doing our sample, you can see right here we calculate a openVDB position that we're currently working on, which is the position of our ray sample point. And then we sample the density there, and we apply that to our Beer's law exponent. And that's based off of Beer's law, and you can go look that up. And it's just a way of trying to apply a diminishing return to a value, and it's especially used in light approximation stuff. And is there anything else I missed? This is simply the volume boundary. I believe I might have moved this to the other function and just called that instead. So I'm not quite sure why I left that there. Yeah, that doesn't even need to be there, so it won't be by the time you look at the actual GitHub repo. And this inner for loop here goes through all of the lights and actually does the light sample for each sample point. So this theoretically can work for multiple lights. Right now, I've only worked with one light, but we do another raycast from the sample point to the light, and we actually make sure that it hits the volume, the actual boundary, which it always should. This should never happen, because if our rays are actually entering and leaving the volume, any point that we sample between the entry and exit points has to be within the volume. And if we go to a light that's in any direction around the volume, it has to be hit at some point. Like the actual point has to be within the volume. So of course we're always going to hit that. So really there used to be an else statement here that would just throw an error, but it's impossible theoretically for this to happen. So maybe I'll throw that in just for sanity's sake. But then we do the same thing where we calculate the number of steps that we're going to need to sample from the sample point to the light, and sum that up, basically. So then we can calculate that light position for where we are actually sampling it, and then sample the volume with an openVDB sampler, and we sum up the sample densities. And then we can calculate the light attenuation and apply a phase result to this using a Henle-Greenstein phase function. I've thought about implementing a couple other of these, but with how long it takes to test each one, because of how slow the ray marching is currently as implemented, I didn't look into that because I was more interested in trying to get everything else all working. So anyway, we then get a resulting color from sampling the light and then taking into account what the background color is, and we can set the resulting value to that. A big failure in this is that it assumes that the background color is always black. So when you're actually calculating the light for each point, you're like, okay, so our background is green, let's say, and then you say, okay, so since our volume is a specific density at this point, and this is how much light is happening at that point from the inscattering and other volume properties of the region that we're sampling, you then apply that change to that point. You can kind of think of it as alpha blending if you've ever used Photoshop. It's kind of like adding another layer on top. So a way of fixing that essentially falls down to, if I put something else in the background, it is not going to be properly applied in this scenario. So basically it always thinks that the background's black. A future change of this would be that you could render your scene normally and then sample the pixels in that resulting render as your background color, and then we could properly apply this. Another big fallback, which I'm not going to demonstrate right now, is that if actually it comes from how this is rendered. So if we actually go to our render, well, actually this would be better shown in a debugger, but for now, since that's not currently set up, I'm going to just try to vocalize this. It's basically this volume. If we run it, it just turns out to be, it's just a quad that's attached to the screen and is displayed last. So everything else is rendered in behind it, and then it finally renders the quad on top of everything. That means that no matter what happens, the objects in your scene won't actually impact the final look of the volume render. And that also comes into play when you're sampling densities and depth, and if something's blocking from the point to the light. That's why that if statement that we talked about earlier, I assume that the sample point always has a path to light, so there will never be anything interacting with that. So if we go, I don't have any objects in this scene, so that would be kind of difficult to show. But that is a big problem of this. And a way of solving that would be to, again, render your scene first and then sample your depth buffer to actually see how far away everything is. And then you can use that in your actual comparisons or ray marching when you go from a sample point to the light to actually see if there is a path from the point that you're looking at to the light. So if there's an object in the scene, you can actually see if there's something interfering with that. Or that will also mean that you can test if your volume should be behind or in front of any active elements or rendered models in your scene. Because right now it will always apply the volume directly on top of the render. We can go ahead and I'm gonna actually cut to render doc. Okay, so if we take a look at this new scene that we have right here, we have the volume, the active region of the volume, and a airplane model that's currently here. We'll show that. So this is our airplane, and then this is with the active display on. Part of the problem with this, as I was just trying to talk about, was the lack of sampling with the depth buffer, and I'm trying to visualize that. So if I go into render doc here, and we look at our draws, these are each of the different, if we look down here, these are each of the different meshes that are being drawn, from top being the first one to all the way through the pipeline. And you can see the different parts of the airplane being drawn until we get to this guy right here, which is the actual quad of the display. And this quad does have a texture attached to it, which represents the actual sphere that we're looking at. So basically what we're looking at here is that parts of the active region, this is a sphere, so it has depth to it. Parts of the airplane should be sticking through edges of this sphere if I was actually properly sampling the depth buffer of the scene. And since that is not currently built into any functionality of the forward render pipeline I have set up in Vulkan, that is something that was left out of this project. So that is certainly something that we're going to be looking into in the future, because obviously fog or a volume shouldn't always be applied to everything in the scene. If there's something in front of the fog volume, it shouldn't be interacting with that mesh at all. But anyway, this is a great little tool to mess around with volume render and openVDB itself. So thank you for taking the time to watch, and I will hopefully speak with you guys again soon.